And thanks for everyone for giving the opportunity to bring everyone together and provide an opportunity to talk and share their information about this the Pyrrhotite research. So on behalf of the team here at UCONN, it's my pleasure to present some information about our research we are doing. So the other two PIs are Professor Crisocco, who is our department head here in Civil Environment Engineering, and Jim Mahoney, who is the director of the Connecticut Advanced Pavement Laboratory. Next slide, please. So those are the typical pictures, and you have seen this already. Those pictures are from the concrete foundations here in Connecticut, and those are severely damaged in those cases. Some other foundations are not severely damaged or not damaged at all and still have pyrrhotite in there. And besides the cracking you see here, the typical spider cracking or the horizontal cracking, what also Nick mentioned, you also see sometimes efflorescence or like a deposit of minerals, this whitish deposits there in the left picture. Next, please. And so our study about investigating this problem started in 2015-16 when we were approached by the Attorney General Office in Hartford here in Connecticut and the Department of Consumer Protection to look into this problem and to see what's causing this. And after studying this for a few months, we determined that the pyrrhotite is one of the main contributor. The pyrrhotite, like in those aggregates which have been used in the concrete to lead to this deterioration of the concrete. And then studying this further, we then received funding in 2019 from UCONN, like internal funds, to look and investigate and develop a test method which then can quantify the amount of pyrrhotite in concrete. And this was then supported with the legislator effort and then a grant in collaboration with the National Institute of Standards and Technology, NIST, in 2020. And you see there 2020, and the topic is risk management of crumbling concrete foundations. So here we focused on the further development on a consistent and accurate test method for the presence of pyrrhotite, and then starting to estimate the future damage, and which led to the second project in 2021, which started like last September, focusing then on the risk assessment framework. Next slide. So the research we are currently in has several steps, and one of the main steps is the standardization of a test method. So the goal is to develop a test method which is minimally invasive and statistically reliable in terms of like how many samples do we need to take to represent, for example, the material in an entire concrete foundation. Step 2 focuses on laboratory testing, where we mix our own concrete, set up a specific laboratory test where we can isolate parameters under controlled conditions. Step number 3 focuses on field sampling, it's forensic testing, to now with the developed test method and sampling to develop a larger data base where all data has been collected under similar conditions, so we can really compare apples with apples. And then step 4 is where all of this effort leads into a development of a risk assessment framework. Next slide, please. So as just as a quick overview, as you know, concrete consists out of aggregates, but also Portland cement and water, which makes them the material. So in aggregates, if we are concerned about sulfur, so usually we don't have any sulfur sources or sulfite or sulfates in there. But as we know, like in those regions which are critical in our talks here right now, those aggregates, they can contain pyrrhotite or pyrite or other sulfite minerals. And underneath you see, for example, an SEM picture of a pyrrhotite aggregate where the light gray streaks are pyrrhotite. Portland cement can also contain sulfur as a source of the calcium sulfate as gypsum added to the cement during manufacturing. So we need to be careful of this when we test for the total sulfur of the concrete, that we are aware that some part of the sulfur comes from the cement as well too. And water usually does not contain any sulfur, but the concrete may be exposed to some sulfur or sulfate sources, which then may be ingress into the concrete. So we might need to account for this too. So when we test in the concrete, so we need to be aware that there might be a base level of sulfate in the concrete coming from the cement, plus there might be some sulfides from the aggregates, plus there might be some sulfur coming from oxidized pyrrhotite, which are coming from the aggregate. Next slide, please. So this is a quick overview. You have heard of this already, but the pyrrhotite, for example, the iron sulfide, oxidizes with the presence of oxygen and water to iron sulfide, and then it forms those oxidation products, which is primarily expensive, and also the releases to sulfate, which leads to the secondary formation of minerals, which leads to the secondary expansion, and all of this, and the sulfate attached too with the hydrogen ions, but all of this is time dependent, and then over time leads to the deterioration of concrete. Next slide, please. So if we look at the aggregates only, and Benoit has already focused on this detail, like how to evaluate whether those aggregates are suitable for the concrete or not. So we would also like use the elemental analyzer. The aggregates would be sampled, would be crushed, would be pulverized, and then the total sulfur amount would be tested. An handheld screening tool, an EDXRF, can be used to, like, if you would be, in a quarry or so, and you want to have a quick evaluation what the total amount of sulfur and so is, to have an indication of whether we have issues with pyrrhotite or not, or other pyrites. This is a good tool as well too. And then with the aggregates, you not only want to know whether this is whether sulfur and other iron sulfides are present, you also want to know whether there is and how much is the chance of being reactive or not, and so whether those metal sulfides are exposed to oxygen and water, or whether they might be shielded, for example. So you could use ion chromatography to accelerate the oxidation and measure the sulfate release. You can use the oxygen consumption method as developed with Benoit's group, and we are involved in this cross-lab testing with Laval University. Here at UCONN we have developed and built oxidation columns. I'll show this in a second. You can also use XRD for qualitative measure, and of course SEM using EDX. Next slide. So here's an example from the method I mentioned just before, like using the element analyzer. This is the type of material in a preliminary study from the Becker's quarry, where we have crushed it and pulverized and then measured the total sulfur. We also have sifted in different fractions and then measured the total sulfur, and you see in the diagram it ranged in terms of the fraction between 0.9% of total sulfur to 0.4 about, but in average it is about 0.6% of total sulfur in the aggregate. Next slide, please. On the right side, on the left side, you see a result from ion chromatography we have run on pyrrhotite containing aggregates, where the surface also has shown already some indication of pyrrhotite oxidation, and the graph below shows the release of sulfates, right, which is it's a reaction product when the pyrrhotite oxidizes into the solution, and you can measure this over time. And the solution is, for example, hydrogen peroxide, which accelerates oxidation, in comparison to control aggregate, which does not have any pyrrhotites or any pyrrhotites at the surface which could react. And you see the dotted line is flat. So this is a method to indicate the reaction rate. On the right side is oxidation column, which has been developed and built here at UCONN, where you see in the picture in the lab, and below is the concept where packed material is being put into a column, and then water is flowing through, and oxygen is bubbled through to help with the reaction rate, and then the release of sulfates in the water can then be measured, and also the ion content can be measured over time. Next slide. The qualitative method, like using, for example, XRT, you see here the equipment we have used, the shown aggregate with the brownish discoloring indicating the oxidation of the pyrrhotite, and it has been pulverized, and then this pulver has been analyzed, and you see the crystal phase identification, and then with the software you can identify it's actually pyrrhotite in there. And also the white deposit in the lower picture had been analyzed, had been scraped off the wall, and then using for crystal phase identification, and you see that, for example, Pyrrhotite was present there at a high amount, and this is sodium sulfate. This is an indication that some high amount of sulfur sources or sulfate sources was present, most likely from internally, from, for example, pyrrhotite, but it also could have been from external sulfate attack going through the concrete and deposited then at the inside. But definitely it's indicative of sulfur source. Next slide. And then you can use SEM. You can visualize secondary mineral deposits like atringite, or as has been shown in other presentation, the thaumasite by Dr. Lehmann, or you see here in the SEM picture like districts of pyrrhotite, and you can also do the elementary composition where you can show like sulfur and iron and oxygen, as Dr. Lehmann had showed before as well too. Next slide. And then the question is, how do we move then from aggregate to concrete, or how do we link this then together? In the end, the question is being asked, like, how much pyrrhotite is allowed in the concrete, or how does it cause and when does it cause deterioration, and how much deterioration does it cause over the time? And this has obviously other parameters are involved in this: the amount of water, or the quality of the concrete, the pore structure of the concrete, the strength of the concrete, for example here, and of course the amount of pyrrhotite or other iron metal sulfides present. Next slide. And so a base concept of our research in terms of the risk assessment is placed on the structural integrity of the walls, or in general of the material then, which is based on the compressive strength, and we start with a certain amount of strength which has been cast in those walls, but then there is a minimum strength required for structural integrity, for example here shown by the red line, and if we have deterioration going on, could it be through cracking or through the development of thaumasite eating up the strength from the CSH phase, then the strength goes down, and at some point it might go below the minimum strength requirement, and this would be the critical time where we then would need to determine, well, those foundations, for example, need to be replaced. So then, and you see on the right side different scenarios. This could be that the strength is not being compromised at all, type 1, or that the strength is somehow compromised over time, but it levels out and never reaches the minimum strength requirement, so it always stays above this, or scenario 3, that it, like, over time it degrades and then it goes under, but it's not, but it will take a certain amount of time, and or scenario 4, where it goes rapidly deterioration and there's no real hope to like stop it or to remediate it. Next slide. And so then the concept behind is that we know there's a certain total sulfur. We can measure this then in the concrete, and this total sulfur comes from the sum of the sulfate. You have the purple line and the sulfide with the reddish line there. And if the sulfide, for example, from the pyrrhotite oxidizes, then the sulfides transfer into sulfates. And the dashed line is the baseline sulfate coming from the cement, which is not of our concern, but the added sulfate, which comes from the sulfide transformation through the oxidation, this could lead to a secondary expansion and then to further cracking and deterioration. So then currently there's a lot of sampling going on. On the right side you see like a table which is provided into the homeowners what kind of total sulfur, sulfate, and sulfides they have, and then also then the pyrrhotite. So it's in general it's a long-term process, as has been said, 10+ years. It's challenging then to quantifying this, so we look for accelerated methods in the lab to develop the model. And also it's very important, as you see with the diagram, the time dependency, to distinguish between sulfates and sulfides currently present in the material. So we do laboratory control testing, accelerator reaction, and field data over time. Next time. So currently we have sampled 90 foundations in Connecticut and Massachusetts. There are, part of those are foundation replacements, and a significant amount are just homeowners' foundations, what we sampled by the drilling technique. Next slide. We have set up a website where, like, anyone interested in having their house sampled for free, they can sign up for this. Next time. Next slide. Then, so we do drill 5 holes in each foundation, about 1 inch diameter, 5 inch deep. We do not compromise any waterproofing, so we do not drill all the way through the foundations. It takes about 60 minutes or less. We don't use any water. We patch the holes afterwards, and then, as I said, within an hour we are out of the house again. Next slide. This is how the tooling process looks like, and also we get like larger chunks into the concrete lab where I can then investigate the statistical variation by drilling more holes. For example, you see there are the 1 inch diameter holes, like the smaller ones, and we core then in the lab also larger ones, but this is not what we do with the homeowners. Next slide. And so we collect the powder from the drilling with a vacuum drill, and then we analyze this powder in the lab. So then we analyze this, for example, with total sulfur. We have done over 1,000 tests, and also we analyze this powder presence in pellets using WD-XRF to distinguish between sulfates and sulfides. Next slide. And then based on this data, we can then start like building a database and then categorize this with related to houses which are more damaged and less damaged and so on, and building up a risk assessment framework. So you see here the preliminary data of this, and it's being built up further. Next slide. And then this is the method I was talking about, the WDXRF, which distinguishes between sulfates and sulfides, which we're developing and calibrating. And the goal is to standardize the sampling method and to standardize this test method. Next slide. And with this test method, since we can distinguish between sulfates and sulfides, we can then also calculate the oxidation reaction process or progress at the time when this, of course, sample had been sampled, and then so you would need to take another sample at another time, and then you can connect to the time history. Next slide. We also evaluate damage with different methods. For example, we're using monitoring crack width and crack length. We are currently exploring using resonance frequency to evaluate the damage inside before it becomes visible, and also surface resistivity, which is an indication of the pore structure and the pore quality of concrete. Next slide. We do, and I only have 3 slides left, we do mix and cast our own concrete in the lab so that we have samples under controlled condition and we know exactly what we put in there. So the goal is to measure the expansion rate at accelerated conditions. So you see here mortar powers, and this is similar to what Benoit has mentioned with the expansion of those mortar powers. And you see on the right side some preliminary data where the mortar bars they shrink, and if they have a high concentration of reactive metal sulfides in there, then the shrinkage behavior is reduced or even like turn around into an expansion behavior, which is indicative of in oxidation or secondary mineral development. So we look at acceleration methods, we look at isolating the phenomena between shrinkage, oxidation, and adrangite formation, and we investigate this under different environmental conditions. Next slide. And in order to accelerate the reaction, for example, we use 3 main avenues. One is the producing our own pyrrhotite through pyrrhotite synthesis, following the method from Professor Powers, and where we run through different temperature regimes, and we have been successful with this. Another method is decomposition of pyrite, which can be purchased into pyrrhotite, and another method is magnetically separating our aggregates, what we have received from the quarry, and then in this case we can increase, and have done so, the total sulfur from 1% to about 8%, which then also accelerates the reaction. Next slide. And this is the last one. So we appreciate every effort and every support we have received from different groups. Here you see a list of different entities we are in contact with, or collaborating with, or talking to and meeting with, and we are very thankful and grateful for their insights and their support. Thank you.
Thanks so much, Kay, for that really interesting talk that shows the rigorous approach that UCONN are taking to this serious problem for family homes.